Synopsys will be presenting our second talk of the day. Paul Stravers, a principal R&D engineer, comes with a wide breadth of experience, including expertise in computer architecture, semi-automatic parallelization, and hardware-software co-design. I swear this man is like the Swiss Army knife of hardware architecture. Today, he will be discussing Synopsys' scalable and flexible embedded architecture, which delivers uncompromising performance for various verticals. So Paul, whenever you're ready, take it away.
Thank you. Right, Joakash. Title of presentation is Meeting Increasing Processor Performance Requirements in High-End Embedded Applications. So what are these applications we're talking about that need so much performance? First, we have solid-state disk drives, where we see in-storage computations coming up, and that needs a lot of cycles. Networking, higher bandwidth, more data processing. Artificial intelligence, well known for its very high MAC throughput, very high memory bandwidth requirements. And then with wireless, on top of all the performance requirements, we still have this very limited power budget. And if you look at these problems, then you can make a case for application-specific acceleration. So these problems that we're looking at are, of course, the ever-growing requirements in terms of performance, but also from the architectural and implementation side, we have problems. Like there are limits to instruction level parallelism and thread level parallelism. And the clock frequencies that we can achieve have been leveled off for a long time already. And there is the case of efficiency. So each instruction that we execute incurs overhead from fetch, decode, dispatch, speculation. Now, one solution might be to do more useful work per instruction. For example, if you take SIMD instructions, they operate on many data items in parallel. So while the operations are standard, add, multiply, what have you, the overhead for each instruction is amortized over the entire vector of data elements. You can also think of application-specific instruction set extensions, where custom instructions replace roughly 10 standard instructions. We call that Apex, and I'll get back to that in a few slides. Or you can even go one step further and have an application-specific instruction set processor, where the complete processor is designed and generated for a particular application. We call that ASIP design, and I'll get back to that as well. Yet another angle, you can integrate application-specific hardware accelerators, which are full custom hardware that's optimized for a particular algorithm or a class of algorithms. And since it's hardware, there are no instructions and therefore no overhead from fetch and decode. What this does require, though, is efficient interfacing with the software and with other hardware accelerators. So in general, what we're looking at is a heterogeneous system where there are different solutions that are tailored to each of the performance requirements. And you can ask yourself, how do you integrate a system that consists of so many different components? So for that, we have the ARC-V3 cluster, where here in the top left, you can see you can integrate up to 12 ARC cores. Get to talk about the cores in the next slide. And those cores, they can have their own caches, of course. They can have their own closely coupled memories for real-time performance. And they can access, through these coherent target ports and the scalable interconnect, a shared cache and a shared cluster memory, which can sustain very high degrees of concurrent access because they are banked. Next to those processors, of course, we were talking about hardware accelerators, and you see them here. We support in this cluster up to 16 accelerators. And those accelerators can have their own closely coupled memories, but they can have their own access through these coherent target ports via the scalable interconnect to that same shared cluster and shared memory. Apart from accelerators, you may also want to integrate I/O devices. Maybe you want to have general access from network on chip. And those closely coupled memories that I mentioned here, need to be mapped in the shared address space. So we want to access them. And for that, we have CCM initiated ports in the cluster. And you can connect also all 16 of those if you have them to 16 ports or a boot ROM or something else. Now, if you're not accessing the local memory and the cluster cache, or the cluster cache needs to be refilled, then you'll probably have to go out either to the NOC or directly to a DDR controller. We support up to 4 of these interfaces. You'll probably have peripherals you want to access. There's trace for debugging, there is interrupt lines and power management. So what this ARCv3 is all about is scalability. We've seen 12 ARCv3 cores in the cluster, 16 custom accelerators, which is surely enough to run multiple software hardware tasks concurrently. There's quality of service so that you can isolate the tasks from each other. And there's multiple clock domains to simplify integration. Bandwidth, scaling up into the terabyte per second region, surely enough again to support high performance accelerators and deep learning networks. Connections can be configured individually. So one connection to one accelerator might be just 32-bit, another one might be 512 bits, 512 bits, very wide. Physical addresses can be configured in a wide range. DDR connections can be wide if you want them, with or without interleaving schemes. 128 outstanding transactions to hide latency in the network. And the high bandwidth shared L2 cache and shared memory allows up to 32 data banks, and they can be up to 512-bit wide and 16 megabyte total size. And that's the upside of the scaling range, but you can also scale down, right? Sometimes you just need something that's low cost and low power. So you just take 2 cores and tiny data banks, 1 DDR connection, etc. It's the same cluster, differently configured. I think what's important is that the architecture here is focused on reduced physical design effort for you, the customer. For example, we implement a single global high-speed data network to carry all the cluster level data communication. So the number of wires actually is pretty much minimum. It's surely enough to sustain that bandwidth, but we don't have wires that aren't very well used. All the wires are used. And nevertheless, with all this sharing going on, we still guarantee bandwidth to implement full task isolation over the shared physical connections. And those can actually be, you have a choice, and you can even mix them, source synchronous channels, asynchronous FIFO channels, or old-fashioned synchronous channels. Now, with so many cores in a cluster, the question is, how do I effectively use them? If you look here to the right, what you see here is a graph that plots number of cores against the total performance. And really what you would expect is that as you, let's say, double the number of cores, you roughly double the performance. So you want to be here on this purple curve, the good curve. Unfortunately, many people trying multi-core processing end up on the blue curve, which is surely a bad curve because as we add cores, you hardly see any performance improvement. And at some point, you actually see performance degradation. And this is happening quite often. So what can we do to get on the purple curve? Well, the ARCv3 cluster is there to help you. But before we get there, you first have to look at your application. The application has to be parallelizable. And unfortunately, this is the case for significant portions of the SSD, the networking, the AI, and the wireless workloads that we started this presentation with. However, you should never forget Amdahl's law, which I think some 4 decades ago, Mr. Amdahl formulated his law, and he said that your speedup will be limited by the serial portion of your program. So with 5% of your application being non-parallelizable, even with infinite resources, you won't be able to get more speedup than 20x. Now, that's the application side. From the architecture side, you need to have synchronization overhead that's really low. So this requires low latency, scalable cluster architecture that is designed for low overhead synchronization. And then you can have your semaphores and mailboxes scale and the use of those scale here along the purple curve. Now, it's not only synchronization. Typically, tasks are also swapping data. So your communication bandwidth's got to be sufficient. And that means that the memory and interconnect architecture is key. Just one curious fact. Sometimes we have superlinear speedups, the red curve. So what's happening? What's going on here? Well, usually this is because the software working set suddenly starts fitting in the aggregate L1 caches. And that gives you an additional boost in performance. It's not very common. So what about the HS68 core? This is one of the ARCv3 cores we're introducing, and that can be integrated in this ARCv3 cluster. So what we're seeing is that it runs the ARCv3 instruction set, which is in the 64-bit version of it, which not only gives you 64-bit addresses, but also 64-bit data and optional Apex custom instructions. The pipeline is 10-stage, has a stall-free load, add, compare, branch sequence that you can execute. Memory architecture, we've seen some of that, L1 caches, and next to the, or actually closely integrated in the processor, you have closely coupled memories, especially for real-time responses. There's a shared L2 and a shared memory. Instruction issue rates 2 per cycle and out of order completion, over 6 core marks per megahertz, 3 gigahertz at typical conditions, 12 core, 16 accelerators, up to 52 physical address bits, an FPU that with a wide SIMD, various page sizes from small to very, very large, hardware managed table, page table, and Linux and Zephyr. A strong focus on memory throughput, 128-bit load store instructions that you can execute back to back even if they're unaligned. There are streaming reads and writes for data with no temporal locality, very large write buffer, very useful with slow peripherals, for example. Many outstanding requests, and also in-memory atomics, which gives you collision-free task collaboration. And that's one of those things that brings scalability to the whole cluster. I mentioned as one of the solutions to a heterogeneous system, or one of the desirable components, an ASIP, application-specific instruction set processor. Now, what is that? What we see here is your algorithm in green and your initial guess at a suitable architecture for that algorithm. You feed that into ASIP Designer. It will give you generated compiler toolchain, and you compile your algorithm, you get firmware, which you can then simulate here on the architecture simulator. And the profile will give you ideas on how to improve your architecture. Maybe you want to add an issue slot or widen an ALU, or maybe remove one if it's not used efficiently. And you might actually also think about fine-tuning your algorithm. You've done that, you make another iteration. Again, you compile firmware and you simulate, you get new ideas, more inspiration, some more refinement. You go around for a couple of times, and at some point you're happy and you generate your RTL. And this ASIP hardware with the firmware executes your algorithm, or even a class of algorithms, of course, very well. You've just optimized for it. And since it's functionalities in firmware, you can have even field upgrades. A big difference with, of course, fixed hardware. The VLIW doesn't incur much overhead from instruction fetch and decode. Such an ASIP strikes a balance between the flexibility of processor and software and the efficiency of hardware accelerators. I got a graph here which plots flexibility here vertically against efficiency horizontally. And well, you'll probably recognize this, right? So at very flexible is your ARC processor with possibly Apex extensions. But the efficiency, of course, is relatively low compared to fully dedicated hardware. But that then again isn't very flexible. And here on this trade-off curve, you can find the DSP and the ASIP, which is actually pretty close to the hardware and still quite flexible. And sometimes it even works to make the ASIP more efficient than the hardware. And the reason really is that you have your algorithm here in the design loop. So the classical flow, you take an algorithm, make hardware, but in this flow, you improve your algorithm as you go, and that might have some positive impact on the final result. Looking at hardware accelerators, two kinds. The Apex is the ARC processor extension, which is your custom Verilog that's integrated with ARC tools into the processor pipeline. And you trigger it by executing an Apex instruction. So it's just mixing Apex instructions with normal instructions. The Apex instructions have direct access to processor registers, but you can't access the memory, so you'll need load store instructions for that. The closely coupled accelerators are, again, your custom designed hardware that's closely integrated into the processor cluster. You control its operation through registers, right? Start, stop, stuff like that. And it has direct access itself through a high bandwidth, low latency, cached or uncached memory. You can, if such a hardware accelerator comes with its own local memory, you can map that memory into the shared memory space so that it becomes accessible from anywhere in the cluster. So now which one should you use? Apex. Use that when you have fine-grained interaction with software. You should probably think about fusing around the equivalent of 10 standard instructions into one Apex instruction. And of course, you have to exclude the memory accesses. Typically, you end up with something that operates on scalar data, like a butterfly instruction for an FFT step or an AES encryption round, something like that. With closely coupled accelerators, you think about coarse-grained interaction with software, something that's able to execute a complete algorithm with its own address computations and memory accesses. And you'll end up that's typically operating on vector data, like a 1K fast Fourier transform engine or a convolutional neural network accelerator. Let's look at an example. This is a SSD controller with probably ability to implement computational storage. So what we see here is that even though this is just one ARCv3 cluster, we integrate two types of ARCv3 cores. So we have here on the right the backend processors, which have an Apex accelerator integrated, and that's actually an I/O instruction engine, and it directly manages the NAND flash from the software that's running on this HS core. On the left, we have the front-end processors, which are much more generic. They're handling host requests, and in case of computational storage, they might also actually run algorithms on behalf of the host. Then in the middle, we see closely coupled accelerators connected to the accelerator target ports and sharing data with processors and maybe also among themselves. And they have also private channels. So you're not limited to what the accelerator target ports gives you. Let's look at another example. We have here an example of communication. So in a heterogeneous system, you have a question of communication because you have to ask yourself, how do I move data between cores of different families, different kinds, different philosophies, even, right? Hardware acceleration versus a software program. So here's one example. So let's think of an HS core here that is going to produce data that needs to be consumed by this ASIP. So what does it do? It executes a function called acquire buffer, and that one specifies where that buffer of this particular size must be allocated. And here in this case, it specifies the ASIP CCN. So that's here. It gets a pointer. The pointer is valid from anywhere in the cluster. And whenever you dereference it, like here, right, the data will be sent to that buffer that we just had. And in this particular case, we see that the processor is executing a filter step. The filter step produces data. It's then dereferencing the pointer P to make sure that the data is stored in this buffer that was just allocated in this remote CCM. After a while, the loop is done, and this core then executes the function release data, which tells the system that pointer P is now containing valid data with this size. And after a while, when the ASIP has arrived at some point in its computation where it needs that data, it will execute P is acquired data of a particular size. Now this P, of course, is exactly the same pointer that we had before, but now it is returned to whatever is running on this ASIP. And this ASIP can now, when it dereferences the pointer P for reads, it has a very low access latency to that data because it's in its local CCM. And this is often what we want, right? Writes are not latency critical, but reads are, and therefore we want to allocate the buffer close to the consumer and not close to the producer. At some point it's done, and it releases the buffer, which then is available for another round of data moves. So, summarizing. We've seen applications that require ever more performance. We've looked at SSD briefly, networking, AI, wireless. There's actually lots of more, much more than that. We've seen that performance can be scaled along several angles. We've looked at multicore, SIMD, APEX, ASIP, hardware acceleration. And I think the takeaway message here that it's all about improving the architecture. It's not just multiplying the same thing many times and hope for the best. You have to improve your architecture. You can also no longer rely on clock frequencies going up. So really you have to come up with something smarter, and a heterogeneous cluster is one of those solutions. The ARCv3 instance of such a heterogeneous cluster can scale to exceptional performance levels. It integrates custom hardware accelerators, ASIPs, up to 12 ARCv3 cores, either all the same or with different configurations, as we saw in this SSD example. It supports high performance synchronization to keep you on the straight line when we're talking about scaling. And it offers high bandwidth data streaming between any type of the components that it integrates. So such a heterogeneous cluster provides really the best of both worlds. And if you map your application wisely to this mix of hardware and software, you achieve efficiency and you preserve the flexibility. Thank you. Are there any questions?
Thank you, Paul. That was fantastic. That's a lot to unpack. So before we get into our audience's question, since I have you, I have a couple of my own. So really quick, by closely coupled memory, do you mean something like scratchpad memory? Or...
Yes, it can be used. Yeah. So, well, the scratchpad suggests a particular use case, right? But what it really means is that that is a small, typically small SRAM that is closely integrated, for example, with the processor, so that you have single cycle load store access to that memory. And because it's software managed, like scratchpads are, it means that you have very predictable responses, not like a cache where you, well, sometimes have misses and therefore unexpected latencies. So in a real-time setting, these CCMs are indispensable.
And I guess kind of in that same vein, then, do you guys usually see your customers include a scratchpad and an L2, or is it either or I mean, I guess closely coupled memory and an L2, or is it either or?
We see most customers that integrate closely coupled memories, either at the level 1, so inside the processor, or shared memory in the cluster. They mostly opt for both cases. So the processor supports a level 1 cache and level 1 closely coupled memories. In the shared cache, it's even better because you don't have to make the choice. The SRAMs that you use for your L2 cache can be dynamically reallocated to shared memory. So if you start with 16 megabytes of SRAM in a very large configuration, there might be use cases where you want to partition that as, let's say, 12 megabyte for the cache and 4 megabyte software managed shared memory. And then maybe 100 milliseconds later, you want to repartition that because you're running another graph where things are different and you want to have different use of your SRAM.
So your guys' program can repartition the closely coupled memory during runtime?
Yeah.
Oh, okay. Oh, that's pretty cool.
Sorry, that holds for the shared closely coupled.
That's
right?
for the shared. Okay, CCM.
Yeah. So the one that is inside the processor, that is dedicated. So you have an SRAM for as closely coupled memory, and you have SRAMs that service the cache storage needs, and you don't repartition that at runtime.
And when you repartition it, you're talking about basically remapping the addresses so that you can reduce cache misses, depending on certain applications.
Yeah, so if you look at the shared cache, then you might certainly be running something that has a large footprint, and then you want to scale up the size of your shared cache. And you can do that. Of course, it comes at the cost of your shared memory at that point. You have to scale that down because the sum of the two still has to be, well, whatever is there in reality.
Right? Okay. So then let's take one from the audience. So is your ARCv3 core ASIL certified? Is it ASIL B, ASIL D?
So we have an automotive version of the ARCv3 cluster and the ARCv3 processors, and it indeed can support ASIL B and ASIL D requirements.
And on a really high level, could you kind of describe what the difference is between your automotive side versus maybe what it would be more standardly found in like those high-end embedded processors?
Yeah, so in the automotive edition supports end-to-end bus ECC, right? So that if you start a transaction on one end of the cluster, you can be sure that what comes out on the other end is really still the same thing that you intended. Yeah. Right? So no bit flipping, or if there is any bit flipping, it would be either corrected or detected. There's ECC, which is also available in the non-automotive version, because if you have large SRAMs, you want to have ECC anyway, irrespective of ASIL standards. Then there is, of course, lockstepping that comes with an ASIL D, so that you can configure your cores in lockstep. And of course, then you have fewer cores, but they will be more reliable. Okay. Those are I think, the major differences.
So since, I mean, even with cache coherency interfaces, protocols, there's still a little bit of non-determinism. How does Synopsys kind of bound that between like your like heterogeneous systems?
Yeah, so I think the fact that we introduce a shared memory is I think one of the most important mechanisms for customers to control what's going on, because what's in your shared memory is under software control. It's not under, well, it's not on demand, right? So where only when you demand it, we start looking whether we can refill the cache or not. But this is something that you can predict. You know that in 100 microseconds, you're going to need that patch of data. So you start a DMA and you make sure that it's there by the time you need it.
Okay. And then also really kind of quick, when you guys have an ASIP, what is the language for the initial guess for the architecture? Do you guys take an RTL? Is it like a netlist? Well, how's the
it's a high level description. So you really don't need to start with Verilog. That would be too detailed and probably would also be very hard to modify, because the trick is that in this loop, right, whenever you get a new idea, you just say, oh, add a function unit. But adding a function unit at the Verilog level is like a 3-week task, right? So here it's just like one line that you add, say, oh, give me another function.
Oh, so we're talking something very high level like System C or MATLAB or something like that.
No, even higher than that. Yeah, it's really it's really block diagram that you have to think of. So you drag another block and say, hey, here's another function.
Right? Okay, so it's like a GUI kind of sort of thing. Like
well,
possibly, like I mean, akin to
the
it.
same abstraction level, right?
Abstraction,
But
okay.
it's still text, because text is so much more easy when you have source code control systems, right? Engineers don't like doing that much. It's more for marketing.
That's fair. That's fair. And then I guess as you have those custom Apex instructions for your accelerators. Is it the processor that's decoding these instructions and then passing on the instructions to the accelerator, or is it the compiler that's disseminating the instructions and the accelerator itself decodes it?
So you mean in the ASIP?
ASIP, excuse me.
Yeah, yeah. So an ASIP is like actually, once you're done, it's like just a standard processor. The only thing that distinguishes it from standard processors like an ARC is that its instruction set is fully tailored to match the application. And our ASIPs are always VLIWs. Now VLIW has as an architecture, as a microarchitecture, has the advantage that you can first, with very low power, very low cost in terms of decoding, etc., you can have many concurrent instructions that you can execute. So for example, you could have 7 or 8 instructions that are decoded per cycle and executed. And you know that 7 or 8 instructions can execute in parallel because you have studied that algorithm, and the compiler that came with ASIP Designer has shown that it can find enough instruction level parallelism for that particular algorithm, so that it makes sense to have such a wide VLIW for that particular algorithm. But you switch to another algorithm, may not make any sense anymore. So then ASIP Designer will basically help you zoom in or home in to a different design, which maybe has only 3 or 4 slots. And then yet something else, you might have 20 slots in a VLIW.
Okay. So, okay. Yeah, sorry, this just kind of blew my mind. So yeah, it's okay. So it's a customized processor.
Yeah.
Okay. That makes sense. Okay.
But it's still a processor, so you can change the firmware and change the algorithm.
Yeah, so it still has kind of like the general purpose. I see now that graph. Okay, sorry, I'm just mind blown kind of moment. And then we got, I guess, one last question, and it's kind of like a fun future looking one. Do you guys plan to add any RISC-V variants of your course in the roadmap, or do you plan to stick with the Synopsys architecture or microarchitecture, the ARC microarchitecture sort of thing? ISA.
ARC has some very distinct advantages over RISC-V. And RISC-V is something that goes by committee. It goes very slow, I think, the development, even though, of course, there's a lot of buzz there, right? But if we run into a customer who has specific requirements, we can very agilely, we are very agile when we respond. If you're bound by a RISC-V framework, then it will be much harder. So I'm not so sure that would be a good idea.
Okay, I think with that, we're running a little bit tight on time. Paul, thank you so much for coming here. This was fantastic. You brought back Amdahl's law. You gave us a walkthrough for instruction processing. This is not only really technical, but it was great to follow. Thank you so much. You did a fantastic job. I appreciate you taking the time and joining us today.
Thank you.
Thank you so much.
Goodbye.